Hey, what's up? It's your old pal, Mr. Cook, and we're going through this test review kind of quick. We got through the first 7 problems. How many more do we have on this thing? Oh boy, look at all that. Oh my gosh, 17 problems. Whatever will we do? Well, we're going to do the problems. That's what we're going to do. I think that's a pretty obvious one. Okay, so we're now on number 8, right? And I see some exponent. I mean, sorry, some radicals. Whenever you see radicals, anytime you see radicals, change them to exponent powers. It just makes it a lot easier to manage. You can kind of like imagine what the path to solving or finding a derivative is going to look like if you have exponent powers. It just helps out a lot. So this square root is the same as saying a 1/2 power. So that square root of x is really the same thing as saying x to the 1/2 power. And then the y square root, right? That's going to be y to the 1/2 power. So it's going to be x to the first times y to the 1/2. That's equal to 1. Now, notice that I have an expression that has x's and y's kind of multiplying together. There's not really a good way to separate the y value by itself like I have over here, number 7. So I'm going to have to use like kind of a different method of taking a derivative, and that different method is called implicit differentiation. Whenever the x's and the y's are multiplied together and there's not an easy route to get y all by itself, this is kind of like the general way that you want to do it, implicit differentiation. Okay, so we treat every variable like its own function, and we do a lot of like chain rule stuff basically. Okay, so we take each derivative separately. So x to the 1/2 power, if I take that derivative, it's going to be a half x to the negative 1/2, because I use the power rule. And then the next thing, I have two things that are multiplying. Now, here's what's important. You need to treat this like two functions multiplying. That means that you do the product rule for this one, okay? So we do the product rule. The derivative of x is just 1. So we take 1 and multiply it times that y to the 1/2. We did this one's derivative. Now let's do the derivative of this one. So the derivative of y to the 1/2 power, I would use the power rule. So I move the 1/2 out front, and then y, and then I subtract 1 from the exponent, negative a half. Now, here's what's weird about it. Whenever you take the derivative of the y part, you have to put, a y prime or dy dt, dx, dy dx, to signify that you've taken the derivative of the main function. Oh man, why did I put dt there? Sorry about that. I don't know why I was thinking physics and stuff. Dy dx. So this is the derivative of y to the 1/2 power. Now I need to multiply on by the other function. That'd be that x. And then that's equal to the derivative of 1, which is just going to be 0. Okay, so now my goal with this one is to get the dy dx's on one side and all the other stuff on the other side. So I actually only have like one term, this one, that has a dy dx on it, because that's the only time that I had to take the derivative of something with a y in it. So I'm going to move all the other stuff to the opposite side of the equation, so over like on this side. So I'm going to subtract that 1/2 x to the negative a half, and I'm going to subtract that y to the 1/2 power as well over to the other side. And here's what I would end up with if I did that. If I moved this over to this side and I also move this over to this side, I'd get, let's see, just the 1/2 y to the negative 1/2 dy dx on this side times x. Let's move the x over here, I guess, so you don't forget the x. I've forgotten the x a couple of times, so that's why I moved it to the front. And then I'd move the other stuff to the other side. So this 1/2 x to the negative a half, which are negative a half x to the negative a half. And then that y to the 1/2, which are negative as well. So minus y to the 1/2 power. Okay, and then I need to get dy dx all by itself, and this stuff is all multiplying on it. So to get rid of multiplication, I would just divide it out. So now I'm going to get my dy dx all by itself here. Negative a half x to the negative 1/2 power minus y to the 1/2 power all over that stuff. So a half x y to the negative 1/2. And you don't need to simplify it any further. Just leave it like that, because all we were after is the derivative. Let somebody else simplify it. Move on with your life. Okay, we are done. There we go. Now we're moving on to a more complicated implicit differentiation problem, and not by much. It's just a little bit more difficult because we have to do the second derivative. Okay, so let's see how this looks. First derivative is going to be pretty easy. We just follow the same rules from problem number 8, and we just do the derivative of each part. So x to the 4th power, that's the same as, if I do the derivative of that thing, that's the same as saying 4x to the 3rd. And then the derivative of y to the 4th is going to be 4y to the 3rd. But since I took the derivative of the y part, I've got to write dy dx over here. And then if I take the derivative of 16, that's just 0. And my goal is to get dy dx by itself to get that first derivative, dy dx. I'll let the pen catch up. There we go. Okay, so let's get dy dx all by itself. So I'm going to move this stuff over to this side. So I've got negative 4y to the third times dy dx is equal to, and then I'll subtract that over, negative 4x to the third. And then to get dy dx all by itself, I would just, since this stuff is all multiplying on it, I would just divide it out. So I get dy dx, so the first derivative, is equal to negative 4x to the third over negative 4y to the third. Now remember how I was saying that, like, don't simplify, don't simplify, don't simplify. When you have to do second derivatives, it's just a good idea to simplify because like what I said with this one is, let somebody else simplify it. Well, you're that somebody else in this case because you want to simplify it because you got to keep working with it. So I'm just going to simplify it a little bit. Look at this. If I have negative 4 on the top and negative 4 on the bottom, I'm just going to divide them out. This is the first derivative right here in simplified form. So when I need to take the second derivative, this is going to be like super easy. So the second derivative, which is denoted like this, d squared y over dx quantity squared, is going to be equal to, and then what I do is I just, treat, again, like the x's and the y's as separate functions. So if it's a function over a function, I'm going to be using the quotient rule for this. So the quotient rule, if you remember from our previous video, is low d high minus high d low over the low part squared. So I'll just, rewrite that stuff. So the low d high, low, and then d high, the high function is x to the third, so that's going to be 3x squared, minus high d low, so that's x to the third. And then the derivative of y to the third power is going to be 3y to the second. But since I took the derivative of the y part, I now need to multiply that by a dy dx. And then that's all over the low part squared, so y to the third squared. Okay, I'm not quite done because I've got this little dy dx here. And you better believe that dy dx is like the same thing as this dy dx right over here. So I'm just going to replace the dy dx with that expression, x to the third over y to the third. And that should do it for me. Let's see what happens, okay? So if I multiply that by x to the third over y to the third, I don't have any more dy's, dx's anywhere like that. It's just saying that I've got this second derivative right over here, and it's equal to like this stuff. And you know what? I don't have to do any more derivatives, so let somebody else simplify the rest of it, right? Let's just leave it as is and move on. All right, so there we go. We got through this ninth problem right now, the implicit differentiation problem. So we got through two different implicit differentiation problems. I think that we'll do this next one, and that'll be the end of this video. And then let's see what we've got left. 11. Oh, now we got a whole other page. Okay, I'll just do it problem by problem. All right, number 10. Find the equation of the tangent line. Ooh, that means something right there. Equation of a tangent line, a line. Well, there are three ways that I can write an equation of a line. There's y is equal to mx plus b. There's also ax plus by equals c. And then there's also y minus y1 equals m times parentheses x minus x1. Now, the top one is called slope-intercept form. That's really nice in like algebra, but we don't really use that too much here because it's a little too much work. And the next one is called standard form, and that's just another version of a linear equation, but it's like really close to slope-intercept form, so we tend not to use that too much here. But in differential equations and multivariable calculus, you'll use standard form for a lot of stuff. The one that ends up like being the most beneficial for you in your calc class is this last one. It's called point slope form, because you're going to be given, in many cases, a coordinate, and then you need to find the slope, which is the derivative. And once you find those three things, you just plug them in and that's your equation. So this is going to be the one that you're going to use a lot. So memorize the formula, but also memorize like how to use it, okay? All right, so here we go. The cool thing is it says, find the equation of the tangent line, that's the template of it, to the curve at this given point. So this is the curve and this is the given point. Well, that given point, that gives us the x1 and the y1, like automatically. So we just plug those parts in. y1 is 0. x1 is pi. Now you just need to find the last little part, the slope. That's the last thing that you need to plug in. And to find the slope of a curve, or find the slope of the tangent line to a curve at a point, that is the derivative. So that means that I'm going to use this thing and I'm going to find its derivative. So here we go, y prime. So this is a chain rule problem, sine of x. Well, I just start from the outside. The derivative of sine is cosine, so I have cosine of sine of x. And then I multiply that by the derivative of the inside. The derivative of sine is, again, just the cosine of x. So I need to find the derivative when the x value is equal to pi. So now I just plug in pi. So let's see here. I've got cosine of sine of pi times the cosine of pi. And this is just stuff from my unit circle. The sine of pi is going to be, let's see, 0. So that means that I'm looking for the cosine of 0. And then I'm going to multiply that by the cosine of pi. And the cosine of pi is -1. All right, now I know that the cosine of 0 is just going to be 1. So it's going to be 1 times -1, which is -1. So my slope, m, is that value, -1. So that's the last part that I need right here. And just like that, I've got the equation of the tangent line to the curve, y equals sine of x at the point pi, 0. Okay, so there you go. That's I think that's a good place to stop. And then we'll just keep going from there. All right, so that's the end of this video. Hope you enjoyed it. Hope it helped you out. And I hope to see you in the next one. Bye-bye.